Okay, so if you're here, you're super early. I just thought I'd start the stream a little bit early so I can just do some testing, just make sure things are the way they should be. And we'll look to make a start. Okay, let's go. Welcome back. Welcome back. I got audio in my ears. That's a little bit disconcerting. There we go. All right. So it is Monday. We are working on a project to automate my live streaming lights. And in the last stream, we worked on prototyping some hardware to effectively mimic what we're going to be building. And that is to ensure that our circuit is properly defined and make sure any bugs that are in our hardware are worked out. So I'm just going to grab a USB cable and we're going to power up the circuit because I did make some tweaks after doing a little bit of research. Last time I did have an issue with the way that I had wired up my LED, but now I have resolved that issue because I was being a bit of a dummy. I was wiring the LED in line with the trigger to the MOSFET, and when in actual fact, what I should have been doing was putting it in parallel to the MOSFET. So let me just power up my circuit here. Give it a moment. And then what we're going to do is we're going to switch over to my overhead scene like this. Right, and we've now got the ESP32 WeMOS D1 Mini hooked up to the logic level MOSFET and also my LED to symbolize the trigger here, right? Because we're going to have an indicator on the module. Remember, this is going to be a 4-channel module. The use case for me is that it's a single channel. So these are going to be attached to the lights, and they're only going to drive the lights. So this is going to be a 1 MOSFET unit, but it can be, I'm going to make it so it can be populated with up to 4. And it'll switch the input voltage, which in this case I believe is 12 volts. And we're going to literally press this button, and our trigger, which is the green LED, that's going to represent the power being delivered to the light, comes on. And we also get this LED on here indicating the trigger. So this red LED is in parallel to the trigger line from the ESP32 to ground. Because it's a 3-volt circuit, doesn't need a current limiting resistor, so we're good to go there. So we've got that set up so I can press the button. I believe I've also got it set up so I can do it via voice. So Alexa, turn LED on. Alexa, turn LED on. Okay. There we go. Alexa, turn LED off. There we go, right? So we've got voice control and we've got local control with this button. So what we're going to do now is we're going to go on and start with our electronics design. And we have to do a couple of things. So anybody who's new to electronics, essentially you have your components and you need to wire them together in order to make your circuit. And the easiest way to do this is to use some sort of design software to, one, do a drawing of how your components are actually connected. This is called a schematic or a circuit diagram. These components, it doesn't really matter how you place these components on this drawing, providing that the wires of each of the components connect properly and that they're wired together, right? That's all that's used for. Next, you need to select footprints, and these are the footprints are essentially what the pad arrangement will look like on the circuit board. And then you need to do a board layout, and it's the board layout that then gets sent to a board manufacturer. And that's where I've got a little bit of an announcement, and I'll wait for people to come in and start chatting. If anyone's in the chat, feel free to sound off. And we're live streaming on Twitch and YouTube tonight. So we've got two platforms. I believe that the chat will be echoed. From what I can see, I'm using Restream, and Restream is echoing the chat from one platform to another. So didn't know it did that. That's pretty cool. Right. Okay. So we are going to use a piece of software called KiCad. And KiCad is a really powerful piece of software. You can do a hell of a lot with KiCad. It's open source. It's freely available. It's you can get it on Windows, Mac, and Linux. And it allows you to do your schematic or circuit diagram. It allows you to do circuit board layouts, but it also has a 3D viewer. And this is really cool because what you can do is you can output your circuit board with all of the files, all of the components on it, and you can bring that into a CAD program and design an enclosure around a virtual circuit board, which you can send that off for manufacturing, and you can be working in parallel to build your enclosure. So when the circuit board arrives, you have something that you can put it into. So that's pretty cool. So that brings us to the first challenge of the evening, and that is that we need a circuit board perimeter or outline. We need to know what we're going to put the circuit board into in terms of its enclosure, because there is, in this use case, it's going to go onto the back of my LED lights. So I decided that I was going to use the battery that came with my lights as a reference. The intention is going to be that the circuit board will go inside here. There will be a port for where the power jack is going to go. And there's going to be a little hole here where a cable is going to come out with a power jack to go into the light itself, a short little fly lead. This battery has, I don't know if you can make that out, but it has like these little teeth. There we go. And that allows the battery to be placed into the receptacle in the back of the light and then pressed down, and then it locks into place. So we're going to mimic those in our enclosure. So this is going to be a dummy battery, but it's going to be the light control. So I need to get measurements from this battery for its outline and its bayonet type fitting, so that we can mimic that, and our enclosure will fit on the back, right? I need to get a board outline. So let's do that right now. We're going to use a CAD application, which I'm slowly starting to learn, and that is a Libri. Now, the reason that I'm not using Fusion 360 is that I only have the hobbyist license for Fusion 360, and my intention is to put this circuit board and possibly the enclosure onto my website for sale. So if I use my personal license of Fusion 360, that does not permit me to make a profit from the things that I design. So I'm going to be using Alibri's Atom 3D, and we're going to build the enclosure in that. I have a license for this, and that allows me to go straight. I can sell all of the things that I make using this software. So if anyone in chat knows anything about Alibri, feel free to engage, help me out. I'm learning, and let's see where we can go with this. Right, so let's create a new component. And before we jump there, what I'm going to do is it's opened up on another monitor, so let's bring that up on my main monitor. All right, so this is the workspace for Atom 3D. It's very similar to other CAD applications in terms that we have this like navigation bar on the left, and it has a series of operations that you can apply to a sketch or a body to make your model, right? So if you're looking to transition or give Alibri a try, you essentially have a little bit of a leg up, especially if you've used other CAD programs. The learning curve is a little bit more gentle than some CAD programs. Some learning curves can be quite harsh. Hey, see you Waffles, how you doing? He says he's here but lurking. Well, thank you so much for the lurk. We're going to go on and get this enclosure, or at least the base layer of the enclosure, defined, so that I can obtain a board outline. That's the main goal for this project, right? So let's go and activate the 2D sketch, and I want to bring in my references. So Control-Shift-P. I'm just trying to force myself to learn shortcuts, right? Because shortcuts are key. So I'm going to place a rectangle in here, and then we're going to define it. So I've literally just drawn a rectangle, and now I'm going to grab my battery. I'm going to grab my digital calipers, and I'm going to get some real world measurements of this battery. So let's zero out my calipers. And okay, so it's 38.7. So have we got a dimension shortcut? If there's one, I don't know what it is. So it's 38.7. Alrighty. And now we get our 70.5. Cool. 70.5. All right, so now we've got our real world dimensions. We're going to constrain this a little bit more. All right, so first and foremost, we're going to center this rectangle on the origin of the drawing. And at the moment, the only way I know how to do this is to dimension the edges of the sketch object to the center point, right? And I like placing the origin of my sketch at the center of the object. That can help further down your workflow when you go to create assemblies and you want things to appear in your software orientated the right way. You know, it's a little bit more predictable. If you kind of drew it off screen over here, for example, and you bring it into an assembly, or next thing you know, it's like it's over here or it's over there. If it's in the origin point, it's bang in the center of your 3D space in the software. So let's select this line on the edge, and we're going to put some math in here because I'm rubbish at doing math on the fly. Thankfully, we live in a time when we got computers that can do this stuff for us, right? So I can put in a formula, 38.7 divided by 2. All right, hit return, and that centers everything that I need, right? Let's pop that measurement just there to make it nice and neat. Now we do the same for the y-axis. Okay, and we go 70.5 divided by 2, hit return, and we now have a fully constrained rectangle in the center of my viewport. And we know it's fully constrained because all of the lines have turned black. So that's good. So this is the outline of our battery. I'm going to deactivate the sketch, and I'm only going to extrude a certain portion of this. I'm going to extrude about, yeah, let's go 8.5 millimeters. So we're going to extrude. And my tool, there we go. Let's change that to 8.5. Okay. So what we're going to do now, I don't know if I can. Okay, we can mirror stuff. Hey, Paul. Welcome in. How you doing? You be watching on Twitch? Yeah, sure. No worries. Hey, Buck. How you doing? So what I'd like to, so this is just the this is just this section here, right? So we've got this object in 3D space. What I'm going to be looking to do now is to put in these this bayonet fitting. I'm trying to get a good light on it. Hey, 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 White Frog. You guys watch where you want to, right? Streaming on YouTube certainly helps my watch hours. So I certainly appreciate the watches. Interestingly, 95% of my viewers are not subscribed on YouTube. So if you're on YouTube and you're not subscribed, why not hit that subscribe button for more content? And trust me, there's more coming. I'm trying to work my magic here to speed up my workflow. Right, so oh, and hit that thumbs up too. See, Waffles, you're so right. You're so right. Okay, so we've got about an 8mm slab that we're going to represent here, but we need to start getting the measurements off of these portions so we can represent those in here. I want to get my circuit board outline, so I'm just working that out. in my head, right? So Control Shift P, it switches on and off my geometry constraints, the view in the viewport. So, see, Frog, I appreciate that. Absolutely appreciate that. So what we're going to do, let us activate the sketch. We're going to put a sketch on this side. This right-hand side represents the flat part of the battery, which is going to apply it to the attached to the, oh my god, words. It's going to attach to the light, right? Okay, so I'm going to roughly draw things out, and then we're going to tighten up the design. I'm literally just spitballing it, right? So that's one of the bayonet sections. And then we got another, and then we've got another one of these weird doohickeys just here. Okay, so have I had a... Unfortunately, I haven't had enough of either, Oi Frog, but you know, it is what it is. So what I'm going to do now, I've got a bunch of constraints on here that I probably need to get rid of because they're not going to necessarily be helpful. So all of these little symbols, they represent constraints. Which if I can check, there we go. I got rid of those constraints. So we're going to apply our own constraints now, just to tie this in. So what I'm trying to show here is that you can be really loose with your sketches, and then you can use constraints and dimensions to snap it into place. So what we're going to do is we're going to model this front section first. We're going to pull that into an accurate representation of what we've got here. So the first thing I want to do is to measure the distance from this edge here to the top edge of the battery. So that is 3.5 millimeters. Okay, so if I dimension this, let's get in to make sure I don't select the wrong things. And that is 3.5 millimeters. Now take a second to compute. All right. Now I'm going to measure the width of this slot. Appreciate you going back and thumbing that. Okay, that's 2 millimeters. So let's dimension this as 2 millimeters. Awesome. Okay, and now I'm going to measure this line here off of the edge here. So with my calipers, that's 1.75. Dimension that to there. That is 1.75. Pop. Okay, so this line here now is fully constrained to where it needs to be in 3D space. So now we've got to start pulling the rest of this sketch into some sort of cognitive shape, right? So first, what we're going to do is we're going to straighten this line up, right? This is going to be perpendicular. So if I select, I'm looking for it, there it is, select this. This is a vertical constraint. So as soon as I click the line with this constraint, it's going to snap it from the angle that we've got into a vertical line. So let's go boop. And bish bash bosh, that's done. Awesome. Equally, this one is a vertical line. Constraint cannot be... Right, so it's already constrained. This one already constrained is vertical. Okay. This one's a vertical. Okay. We're getting there. Now, this line is what's called collinear with this perimeter of the battery. So, let me see what we got. Collinear constraint. So we select this line, and that snaps to it. Okay, good. Good. Right, now we need to get some measurements of length, and then we'll start to see these lines turn in black as they get fully constrained, right? So, I'm going to measure from this node here to the top line, and that is 9.75. So let's dimension that vertice. Come on, let me dimension that vertice. There we go. I didn't have the vertice selected. Okay, and it was 9.75. Okay. So I'm now going to measure this little slot, this little line here on the battery, and see where that comes. Okay, I believe that's 4.5 millimeters. Bosh. Look at that. Okay, that's good. Okay, and now this line here across the back edge. It's hard to see. Okay, 15.45. 15.45. Okay, cool. Now, how big is this section here? That measures 12 millimeters. Okay. So that's the first section done. Let's quickly do the rest. Should we just move quickly through this? I think we should. So we're just going to apply some constraints just to pull this into the shape that we want it. We're going to bend the sketch element to our will. And I'm just quickly taking measurements. Okay, this is collinear with this edge here. Now, here's the all-important measurement. What is that? What is that measurement? 6.5 millimeters. Okay. We're moving through this now. That's 10 millimeters. Okay, so we've now got a fully constrained second section. And I'm imagining that we're going to be able to grab some of these measurements off here, but okay. You guys, way, Control Z. Don't want to see that. Okay. If it was symmetrical, possibly, but if I show you this, it's not necessarily. I know what you're saying, right? Doing like a linear pattern sketch. But if I show you, so if this was like a mirror of this, you could mirror it. I suppose if we know the distance between this leading edge and that leading edge, we could probably pattern it. Okay, let's try that, shall we? As I say, I am learning Libri. So we're using, for those of you who don't know, we are using Libri Atom 3D. I've not used this tool before for patterning. Helps when you're on the right scene. We're going to select our sketch objects. Okay, first direction. Okay, cool. And how many millimeters is the distance from the top of one to the top of the other? This could be a game changer. 38. It's definitely a time saver, right? 38 millimeters. So if I say 38 millimeters, we've got the second one there. Hi, Frog. You ask your questions. You ask your questions away, right? That is absolutely why I stream. So feel free. So what I'm going to do, I'm going to measure the distance between this element here and this element here, and if it's the same real world as is in CAD. It's about 3.4 millimeters, so it's probably going to complain about being over-constrained, maybe? $3.25, that, yeah. For our purposes right now, it's okay. Okay, Oi Frog asks, has someone not already done this for a 3D design, or do you want to do it yourself? So, Oi Frog, what we're doing is we are building an enclosure, right? I'm going to make a circuit board. So I've got this ESP32 Wemos D1 Mini, and what I'm making here is a 12-volt voice controlled lighting controller, right? So we're going to have up to 4 outputs that we can control. For the lights, I only need 1. So we're going to design a circuit board in a moment once we get our board outline. But I want to make it so that it fits inside a bogus battery, right? So there's like these little indents in here that I need to take into consideration with my board outline, especially if it's going to sit inside here. And then once I've got my board outline, I can go ahead and start working the circuit board itself. So yeah, we're making a custom enclosure for this module, right? So if I got, it would have been really nice if I could have adjusted. Can I dimension this and just fine tune it maybe? 3.5. Is that gonna? Oh yeah, it'll allow me to do that. That's pretty cool. Okay, so if I now deactivate my sketch, and what we're going to do is we're going to remove some material. We're going to do a cut operation, and the depth of cut. Let me zero out my calipers. The depth of cut is going to be 2.2 millimeters. Minus 2.2. Okay, so there's my slot. Now I want to mirror this. And I've never done this, right? Nolan! How the devil are you? Long time no speak. I hope you're well. Okay, let's bring in my 3D reference. And then what we're going to do, we're going to do a mirror. And we want to mirror, yeah, we want to mirror this extrusion. And the mirror plane is going to be here. Wow, that's so cool. Right, now we've got, a few people into stream. I'm going to make a little announcement. So tonight's live stream, we actually have a sponsor. Big thanks and big shout out to PCBX. PCBX is a board manufacturing company who have reached out to me and asked me if I would be interested in them making some circuit boards for me. So PCBX, if you check the links, if you're on YouTube, if you look at the description, there is a link to PCBX. On Twitch, if you go to my About section, one of my panels will show the PCBX website. Let me just take a moment to talk about PCBX. So PCBX, as I say, there's if you're interested in making your own circuits, it's really important that you have a means. Thank you, Buck. Appreciate it. It's really important that you have the ability to make your boards. Now, whether that's through acid etching at home, which use nasty chemicals, whether that's using a desktop CNC where you're cutting out copper and making sure that you have the correct depth of cut so that your traces are isolated properly, and the ability to apply a solder mask. Add into the mix having multi-layered boards can get really complicated with your own vias. It becomes incredibly convenient to use a board manufacturing company. There are a number of different board manufacturing companies which you're well aware of, each having their own unique selling points. PCBX has a unique selling point in that it has an online EDA. Buck, we're at the early stages of the conversation around sponsorship. Right now, we're just having a look at what the boards look like. I'd like to work with PCBX a little bit more, but this is just doing a bit of a handshake to say hello, how do you do? And we'll see where this goes. So, as I say, if you don't have a piece of software that you use to design your circuit boards, PCBX have an online CAD program, which allows you to build your schematic, to do a board layout, to see your circuit in 3D, and then obviously directly order from the application. They offer the usual sort of features that you would come to know and expect from a board manufacturing company. So you get your 1 to 4 layer boards that can be manufactured. They will also do assembly. You can use their assembly service whereby you upload your schematics and your board files along with a bill of materials, and they will quote you for a completed board coming back to you. And all of this information is available on PCBX. You can have a look at the different manufacturing techniques that they use. You can also look at the components. So if you want to look at your bill of materials and you want to search to see whether or not they carry the components that your project takes, you can have a look to see how much these unit costs. So give PCBX a click, have a look at their site, and if it's something you'd like to try, I'm sure PCBX would appreciate your support. And thanks to them for offering to make the circuit boards for this project. And may this be the first of many. Right, okay, so back to the action. We now have our board outline. Sorry, we have our battery outline, should I say. And we're going to leave it there, right? We're not going to go too daft in terms of the amount of effort that we're going to go. So I'm going to put a sketch on this top surface here. And I'm wondering whether or not I can project. I can project to sketch. I can indeed. Excellent. Right, so I want to project these entities because I want to see where the indents are. Oh, thank you. Thank you, Buck. Appreciate that. Okay. Entities to project. Ooh, maybe I'm not using this tool right. Project to sketch. Copy selected figures into the current or a new sketch, model geometry, reference geometry, and other sketches can be selected from the projection. Okay, cool. So I should be able... Can I select that? Why is that not showing up in project to sketch? Ah, there's more than one way to skin a cat. Okay, so how do I get to my reset view? That's it. That's what I want to do. There we go. Okay, so now I can see where these indents are. So if I want to sync my PCB into this section, because it would make sense to do that to save space. What I've got to keep in mind is that the wall thickness of this bit of geometry here needs to be taken into consideration. So let's go ahead and we're going to put a rectangle in here. So what we're doing now is we're creating our board outline, and then I promise we're going to get on to making a PCB very shortly. So let's create a rectangle, like so. I want to have 2 millimeters from this top edge. I want 2 millimeters from this bottom edge. And I want 2 millimeters off of these edges here, simply because I want that tolerance for Would you just believe it? Control Z. That projected sketch element shouldn't have moved, right? Okay, so what we're going to do then, if I dimension that line there, constrain it like that, it shouldn't move anymore. 2 millimeters. There we go. Right. I personally like to fillet the corners of my boards. That's a little bit of a stylistic thing that I do with all of my circuit boards. Good example is this board here that I made for my streaming controller. All of the edges are rounded, and it just makes it not... I mean, circuit boards aren't intended to be handled because they go inside enclosures. But for the person that's assembling them, it's nice to not have really like sharp edges. So what I like to do is to fillet the edges of my objects. So we're going to fillet this and this. And let's fillet it. Let's go a 2 mil fillet. Okay, no, let's go 3 mil fillet. There we go. Awesome. Now, I don't know if I can do this. I've messed up with this type of thing before, right? So I want to see if I can fillet more than one set of sketch lines. So if I select this and this, can I... see, it's reset. So it looks like I've got to fillet the edges one at a time by the look of it. If I apply that. Apply that. Apply that. You can apply that. Okay, so now we've filleted our corners. We need some mounting holes. And then what we're going to do is I'm going to put in some holes for screws. So we're going to use 3 millimeter screws. So if I just hit the dimension, I want to dimension this, make this 3 millimeters. Now, I'm not defining the actual hole dimensions. I'm defining their position. We will set the mounting holes in the CAD software for the circuit. Right, and that's going to be 3 millimeters. And now we just need placement. So let's go. If I say 4 millimeters. Oh, what? Control Z. Okay, let's measure you from there. Okay. I would have expected those sketch elements to like not move, but okay, I'm going to try and focus on the circuit board right now because at the moment the sketch is a little bit floaty. Stop it. Stop it. Stop it. Right. Okay. Collinear. There we go. There we go. All right. Dimension this with this, and we're going to do 4 millimeters. This and this again. We're going to go 4 millimeters. Please stay. Please stay. Oh, thank goodness for that. Right. Okay. And now if I deactivate the sketch, right, I've got my board outline. So if I right click this, I shouldn't be able to export it as an SVG. We'll click on OK. And if I go to documents, projects, ESP8266, and this will be board outline. Okay. That's that bit done. So we've now got our board outline. We're prepping for a little bit of work ahead of time, right? So what we're going to do now is we're going to work on our schematic. So the schematic itself, let me just bring up this. So we're using an ESP12F module. And this is what we need to create in a circuit so that the ESP12 can function. This is what's called the minimum wiring diagram for the ESP12 module. Essentially, we've got the reset and enable pins pulled high to 3.3 volts. So this is a 3.3 volt device. You put 5 volts into this. It's not necessarily going to release the magic smoke, but you're not likely to be able to use it much after that, right? So anyway, we run the reset and enable pins through a 10K resistor to 3.3 because we can pull these to ground and we can either disable the pins or we can reset the device. So the 10K resistor allows you to do that, pull pins to ground without creating a dead short. Create a dead short, that will release the magic smoke, unless there's something current limiting in your setup. Over on the other side, we've got another 10K resistor to GPI 0, pulling that high, and a push button to pull that to ground. And that ultimately is that's a button that we use to put this into programming mode. So if we want to program this module, we either have to be able to pull GPIO to 0 to ground through a programming board itself or by pressing a physical button. So we're going to probably use a physical button in this case, especially considering we're going to make this available for sale, right? GPIO 15 needs to be pulled to ground, and that's done through a 10K resistor. And then we just need a button on the other side, as I say, to act as the reset button. So beyond that, what do we need? Well, we need an LED, we need a button, and we need a logic level MOSFET for each of the channels that we are looking to drive with this system. So let's see how we're going to do that. So we're going to open up KiCad. Where's KiCad? So many windows. All right. So this is KiCad. And I've just gone ahead of time, and I've saved a project, so we can just get straight in here. So we're going to open up the schematic editor, right? So this is where we create our schematic or circuit diagram. And remember, this is a visual representation of the board. Okay, so we just get like a draftsman template, and all we do is we grab components and we lay them out in a visually pleasing way. But remember, this is not how things will play out on the PCB itself. So let's go ahead and start building our circuit. This is the fun bit, right? everything's been a bit of a chore up until this point, but this is where we start getting a bit creative. So we're going to place a component. So we go to the place menu, add a symbol, and then it searches through its library and gets an itinerary of all of the components that KiCad knows about. If you're trying to use a component that KiCad doesn't know about, there's two things that you can do. You can do a Google search and look for a KiCad library for the component and footprint that you need, or you can design your own footprints and components to get you moving. And that's I would say that's more of an advanced topic to cover. So we're not going to be covering that in tonight's stream because we'd still be here in a week's time, right? It's a rabbit hole that you can go down to your heart's content. So we're going to search for ESP12. Let me see. What have we got? MCU expressive controllers. What do we got? Anything? ESP12F. Okay, so we're not really getting a result. 8266. Okay, let's have a look. There's too many pins on here for this to be correct. So we've got a WeMust E1 Mini. That's the actual module. So if you wanted to use the module, we could just drop this in, but we don't want that. We just want the chip. Now, here we go. RF module, ESP12E. Which one are we using? Let's find the one we're actually using. Let's get the component out of my parts bin. Let's fire up the microscope, and we're going to do a positive ID on the microcontroller that we're going to be using. So you could go down to the component level if you really, really wanted to. But Expressive make these really convenient packages or modules that we use in our projects. So they're really helpful because it cuts down the time. And the ESP the ESP32 or the dev kits, they're another layer above that, right? So okay, so let's go over to the microscope. And of course, the microscope scene doesn't want to play ball. Okay, let's see if I can fix this. One moment, please. If I go to the studio. There we go. That's more like it. All right, so this is an ESP82, sorry, ESP8266 MOD. So it doesn't really help us much. We've got a bunch of GPIO pins on the back. I'm reasonably confident. I'm looking at the pinout. I'm reasonably confident this is the correct library for this module. You do have to be a little bit careful, making sure that you get the right module, the right footprint and package in your software, right? But I'm more than happy to use this. We can always print this on a piece of paper, right? And before we send it out to anybody. So we're going to take that and we're just going to go plop. I'm going to just pop it there. Now, what else do we know we need? Right, we know we need resistors. So let's get a resistor in here. Wow, I didn't expect there to be that many components like this. Right, so I'm going to choose that. There we go. There's my resistor. I'm going to place another symbol. I want a switch. Okay, maybe a button, maybe? Oh, wow. Okay, let's manually find it, shall we? Let's collapse some of these things. Where on earth is that? All of these menus seem to be... Can I right-click and collapse? There you are, device. Goodbye. Right, okay. Well, that kind of baked my noodle for a moment then. Switch. What do we got in here? Coded. Dip. Push. Push. Simple push switch. There we go. Perfect. Let's drop that in there. Let's double check our diagram here. So we got resistors, we've got push buttons, and we've got power, right? So we need power of some description. Freaky! Welcome into chat, buddy. How you doing? Hope this Monday is treating you well. So we need to put some power in here. So let's add a symbol. Oh, there was a menu item there specifically for power, right? So let's add power. We want 3.3 volts. Let's add one of those. And we want a ground. Perfect. All right. So what we're going to do, we're going to mimic this drawing to this module, just to give us the basic setup, right? So we know we need 3.3 volt inputs coming in. So all we do is we'll grab this and we'll choose M for move, bring it over here, put one there, and we'll copy paste, put one there, and copy paste one there. And this doesn't have to be pretty right now. Well, Freaky, I hope you're feeling better soon, buddy. We know we need at least one ground. In fact, let's have a look at that diagram. We've got 4 grounds that we need. Okay. That sucks, buddy. I hope you're feeling much better soon, right? That's it's no good when people are sick. Okay, 1, 2, 3, 4, 5. We got 5 resistors that we need in this. So let's bring 1, 2, 3, 4, 5. Okay, and we know we need 1 push button move and then copy paste there. So then let's start hooking this up. Let's wire this up. So we got a bunch of tools on the right hand side for wiring. I'm going to add a wire and literally just zoom in and click and connect that. Easy. Easy. Oh, what's the symptoms, Freaky? Okay, so what are we going to do? R1 we're going to put into reset, R2 into enabled. That's what I think we're going to do. Are you just like tired and lethargic? Because if that's the case, I mean, I feel like that every day. Okay, and then this one goes into the enable pin. And now if I grab my 3.3 reference, if I pop it in between here, I can just connect these over like that. Now, when you see a little dot like this, it means that the wires are connected. If you go over a wire and there's no dot, they're not connected. Ah, man. Well, as I've already iterated, I hope you're feeling better soon, buddy. Okay, let's move this text. I want to put this text the other side of the button. All right, so we'll pop. I'm going to pop this down here because I don't know whether or not I'm going to be wiring the GPIO pins over here on the left-hand side of the microcontroller. So I'm just going to, for convenience, just move them out of the way. All right, so all we need to do now is we need to line this up a little bit, so it needs to come over. So I'm a little bit silly in that I like things lining up, but you'll see what I mean about lines joining in a second. Okay, so you'll notice that this line crosses the enable pin, and where it crosses this reset pin, we've got a dot. So that dot signifies that these two wires are electrically connected. The fact that there is no dot here means that they are not connected. So that's something to bear in mind, especially if your intention is to have things like electrically connected. Do you know what? I don't think I'm going to be using them, or am I? Oh gosh, I'm thinking. We'll leave it there. It's fine. All right. So what we're going to do is connect the main ground of our microcontroller. So right now our microcontroller's got 3.3 volts. It's got ground, so it technically has power. We've got 3.3 volts pulling it up on the enable pin and also the reset. So it's not quite there though. It's not going to be operational at this stage. So let's have a look. We've got GPIO 0 gets pulled through another resistor. So we'll pull up resistor number 3 for this job. Okay, and in fact, let's bring these a little closer, like that. All right, but we'll notice that that gets pulled to ground. So I might, in fact, that's exactly what I'm going to do. I'm going to pull this over to the right. I want to build some room here. Perfect. Let's delete these a moment. Let's put a new line in. Like that. Okay, let's select our switch, rotate it by pressing R, and then move the switch in line. Let's bring a ground reference in. And now we'll just draw a line from the switch to connect the circuit, and then that to ground. So we now have the ability to put the device into programming mode, we need to pull GPIO 0 to ground at boot time for it to say, hey, oh, you want to program me? Okay. So without that, we can't. Oh, right. So we got another resistor here. So I was a bit premature in putting that ground line in. So let's get R4. I'm sure there's a Star Wars reference in there. And let's connect the resistor to the switch and the resistor to ground. Awesome. And then finally, we need to grab our final resistor and put, I think is it GPIO 15. In fact, let's just tug this over to the right. Just to give us a little bit of room, should we want to use that. GPIO 15. And then that to ground. Perfect. All right, so this ultimately is our microcontroller now wired. So is this where we want it to be? No, because we've got some LEDs, some buttons, some MOSFETs to wire in. So I just realized we are going to be using some of these pins here, I reckon. Some of these GPIO pins. Definitely. Okay. So let's go ahead and grab this. And we're going to move it to the right. I want a little bit of room to be able to label things the way I want them. Let's reestablish our connections here. So the enable pin to there, that to there. There we go. Good job. Good job, good job, good job. Okay. So what we're going to do now is we're going to put some wires on all of our pins because we may or may not be using them. But if I put wires on them, it means that I can just randomly choose the pins that we want to use. You do it! Hey, buddy, welcome in the stream. We're live on both Twitch and YouTube. We're everywhere. So right now we're building a 12-volt switching, a 4-channel 12-volt switching system. The circuit that we're going to actually populate and build is for my lights. And I'm going to have them hooked up for voice control. And it's just so I can get everything trained nice and cleanly on my workstation. I'm working hard here to try and get my workspace, the limited space that I do have, I'm trying to get that working for me, not against me. So this is all about efficiency of my space. And right now, it's not that efficient. I see your shed build is coming on, buddy. I'm digging the lights. Did I read that right? That Mrs. You Do It picked those out? Okay, this dog leg in this wire is triggering me. Right. I hear you loud and clear, man. I hear you loud and clear. That one kind of hits. We've all got life experience, right? So we're going to put some labels. We're going to put some labels on these wires, because the really cool thing about a schematic or a circuit diagram is that you can just like put a post-it note on wires to say this connects to that, and the software just knows that that's what you're trying to do. So when you build your board layout, you have to make them connect, but for our schematic, not so much the case. So there are two lines that we need that we can just put a label on straight away. So first of all is can I add a label to this net here? And it's going to be TX. Okay, so we've got TX there, because if I zoom in, right, we've got TX, and this is for transmission of data. So ChatGPT is not quite there, right? So I'm now going to connect a new label. This is going to be RX. Mind you, some of this AI stuff is pretty impressive. I gotta be fair. It's going to be a bit of a paradigm shift, especially for a solo creator like me. So all of my produced content on YouTube is shot by me, is edited by me. It's pretty much all of, it's all me, right? I do all the thumbnails. So things like AI can help me speed the process up as a solo creator. So, the Track Nerd, welcome in. Right? No worry, iFrog. No worries. Okay, so we've got TX and RX. This now completes the microcontroller side of the circuit. We have power coming in, we have ground, we have all of the pins pulled to their respective places, either pulled high or pulled low, and we have a TX line and RX line. So these we are now in a position where we can, we could design the circuit for this and program it. So, what else do we need? Let's add some more components, because we need to figure out MOSFET. And it's an N-channel MOSFET, so let's select that and just drop that on there. We need an LED. Okay, just a bog standard LED. Like that. Awesome. No worries, you do it. Appreciate you, buddy. Good speaking with you. Appreciate the alert. Okay. So we also need a push button, right? So let's select this push button, and we're going to copy it, and we're going to paste over here. So, how is this going to work? We need to reference our prototype, right? We've got to reference our prototype. So we've got a button that connects to a GPIO pin. And in this case, we've got D1. Button on D1. Unfortunately, now this is the thing, right? That kind of messes with my head. We've got the GPIO pins, but the WeMOS has like data pin references. D1, D2, D3, and they don't show on here. So it's like, huh? This hurts my brain. And every time I work on this sort of stuff, it's like, oh man, seriously, what have I got to do to make this work, right? So, the thing we got to do is do a Google search, right? We're going to do a Google search for a WeMOS D1 Mini, and we're going to say pin out. And we're going to switch this to images. And then we're going to pick the WeMOS that looks like what we've got. And now we can see the GPIO pins, right, that we're going to use. So let's have a look. What we got? We've got, I want to stay away from TX and RX. I want to try and keep those free if I can. So we've got GPIO, we've got 1, 2, 3, 4, 5, 6, 7, 8. We got 9 GPIO pins. We need 8. So we've got 1 spare. So let's decide to have the buttons on one side of the microcontroller and the MOSFETs on the other side of the controller, just for one side's input, one side's output. Let's do that. And that way we can kind of figure things out. Keeps it nice and clean in the brain. Whatever it takes for you to keep thinking straight, right? So we're going to put some labels in here. So GPIO 5, 4, 0, and 2. They're going to be well, that's just marvelous. GPIO 0 is already being used for our pull down, right? So could we use that? I don't know. Shall we find out? I think we should find out. So let's bring this back in. Let's put our button on GPIO 0, which was, what pin was it again? GPIO 0 is D3. D3. It's all right. Old man eyes. Let's unplug this, and we're going to plug in the button to D3, like so. Okay, so that's GPIO 0, which is also our reset button, which is just here, right? So let's power this up and let's program it to see whether or not we can use this as our button. All right. Let me find the LED. You know what? I have no idea what its IP address is. Okay, I'm just connecting to it. Let's get the logs in console. IP address 37. Okay. So let's jump over to... Cool. Here's our LED test. Right, let's configure this. Configure module. And if we turn that to none, GPI 0 is a button, and then we save the configuration. So hopefully, now when I press this button, yeah. All right. Okay. So I have a sneaking suspicion that we can use this GPIO 0, which would normally be used to put this into programming mode. I reckon we can use this GPIO 0 as a button for us to trigger. So that's one less component that we need to have in our setup, which is cool. I like. This is efficiency. So back to Wemos, GPIO 5. Okay, so we want to put a label on here, and this is, let's call this I don't want to go button. Yeah, let's go button A, B, C as opposed to 1, 2, 3. So BTN. So if switch 2 is A, this will be button B. And let's go on GPIO 4. BTNC on GPIO 5. And then what we got? GPIO 2. Button D. Okay. Awesome. So what we can do over here now, right, is we'll grab a ground wire or a ground component, copy it. We'll put a wire off the top. And then we'll put a wire there. Okay, and next thing we're going to do is we're going to rotate the text. Alrighty. And then we're going to duplicate these, right? So we're going to kind of copy, paste. Paste. Okay, so we've already got one button over here that we're going to use, and now we're going to use these 3 buttons to make up the other 4 channels, right? So we want the labels. So BTNB. Can stick that on there. BTNC. Rotate, put that there. And then BTND. And rotate and pop that there. Right. So now what's happened, in fact, I'm going to, just to keep this nice and clean. I'm going to put this over here, right? So when I zoom in, you can kind of see what's going on. So these essentially are now symbolically linked. So button B, this wire, actually comes over to GPIO 4. Button C over to GPIO 5. Button D over to GPIO 2. And we already got this button just here, right? So that's awesome. Now we've got to get our outputs. Okay. And we're gonna do the same naming convention. Let's have a look. We want 16, 14, 12, 13. Right, so 12, 13, 14, 15, 16. Okay, so we can use any of these from 12 upwards, 12 and above, right? So let's go label, and we're going to go MFET A. So for MOSFET A. And we'll go MFET B. MFET C. And MFET. So we got a Houston, we have a problem. This one's already in use, right? Pulled to ground, so we can't use that. So we'll go and add a wire to GPIO 16, and that's going to be MFET D. Click OK. Plop. Just like that. Just like that. Okay, so what we did with these buttons, we're going to do with the MOSFETs. So let me remind myself of how the MOSFET is wired. I always forget. See, I don't know if you're like anybody else. One of the things that I do a lot is forget what the symbol means and how it needs to be placed in a circuit, all of that sort of stuff. So one thing I know is it's an N-channel MOSFET. I can do a Google search to find out the particulars of this MOSFET so I can wire it correctly. I can also look at my hardware and see how I've got it wired. That's another way of doing it, because I did this previously, right? It's a common thing, right? Where you'll forget stuff. So I'm sure it's pin 1, 2, and 3. So pin 1 marks our trigger wire. So pin 1 is our trigger wire. So let's draw a wire from there on the trigger. Okay, oh, in fact, let's bring in our LED. We're going to put this in parallel. I'm going to figure this out. How is this going to work? So, oh my word. How do you wire an LED again? Oh my God. The flat side is the ground, isn't it? So that needs to be rotated. That's the positive side. The bar marks the ground, if I'm not mistaken. Can somebody confirm that in chat? And what we're going to do is we're going to bring a wire in here between these two devices, like so. And then we're going to put another wire like that. Okay. And this will be, I don't know, this will be MFET A, right? So MFET A. We'll put that label there like so. Okay, so which pin goes to ground? So pin 3 goes to ground, which is kind of handy for me because that means I can kind of do this. I can go like that. I can grab a ground from over here. I can rotate it, put it by here, and then I can draw a wire to there, and that connects my LED. Ooh, you sound like you're having a party, iFrog. That's the sort of party. That's the sort of party that I want to be involved in, right? Okay, so we're going to put a label on here of Chan A. For channel A. All right, so we put a trigger on MOSFET A. That turns the LED on. Oh, is it really? Well, there you go. I'm obviously not a connoisseur, right? Who knows with these drinks names? You see, you just exposed my naivete. Ah, I did not know that. You've educated me. All right, so that's our output channel sorted. We're getting close to starting to require a board layout. Okay, so yeah, you educated me. So we're going to copy this each of the channels that we've got. And I'm going to put them down in this bottom corner. Okay, so there is our outputs. So we've got our buttons, we've got our outputs. Now what do we need? We need a means of getting this actually out, right? So we'll need a connector of sorts. So let's place a symbol. So we need header pins. Okay, so let's see. We've got 4 channels. Each channel needs a ground and a power. So we will say 2, 4, 6, 8. We need an 8 by 1 pin. Okay, we'll click on OK. And then we rotate. Place it there. Actually, let's rotate it the other way. And then can we flip it? Flip, like that. Cool. Okay. So this is our output. And let's just draw some wires on here so we can put some labels in. Okay, so the first thing we're going to do is we are going to get a ground. We're going to copy that and just place it there. And at which point we're going to... Every odd pin is going to be a ground wire. Okay. 2, 4, 6, and 8 are going to be our outputs. So if I grab my label and I just place it here. Now I've got to do some updates here. So this will be channel A, this will be channel B. That's actually a good point, right? I need to make sure all of the elements that I copied get updated. This will be MOSFET B. This will be MOSFET C. This will be channel C. This will be MOSFET D. And this will be channel D. Awesome. Okay, cool. Let me just check my buttons are wired and labeled properly. They are. Right, so there's channel A. And all I got to do now is just grab my channel labels. And I can just drop them into place. And channel D. Okay, so we've got an elephant in the room that we need to address. All right, let's hit the save button before we lose everything. Okay, we got an elephant in the room. And that is that the system, while is we're almost there, right? But not quite. The reason that we're not quite there is that we have no power delivery at the moment. No need to be rude, huh? What do you mean, Oi Frog? So we have no power delivery. We've said that we've got 3.3 volts, but we've not really told this circuit where it's getting 3.3 volts from. Oh, the elephant. But you're a frog. You're not an elephant. Have you got an identity crisis? Okay, so we're going to add a symbol. And we want a barrel jack. Just have a look. Okay, what about power jack? DC jack. There it is. Look, let's have a look. Let's see what we've got. DC barrel jack. I mean, we've got a symbol, right? You bought? No. So we are using existing system. Let me show you what we're using. Alexa, turn video conferencing lights off. So at the moment, my lighting system works by switching mains voltage. And I've got a series of sockets mounted up here. And I've got this jack here that needs to connect to the back of the light. in some way, shape, or form. So this is the power supply that we're going to be using. What I want to do is untether it from the current system because, like I say, while it's functional, it's less than desirable because it means I've got cables strewn all across my workspace. It looks absolutely horrific. So we're making these lights independent. At the moment, they're stuck in their positions because of the length of cable that they have available to them. Alexa, turn streaming lights on. So with this modification, what's going to happen is that the battery module or the battery receptacle on the back of the light will take this control module, and then I can place these lights wherever I want, and they will still work as these smart lights. So that is no. Oh, Frog, it's always good, right? It's always good to think outside the box. But there is a specific design goal that we're working towards. So I think I've got these barrel jacks that we're going to be using. Let me see if I can find them. They are in my parts bin. Here we go. So these are the barrel jacks that I'm going to be using. As he drops it on the floor. I think that's a decent representation. This barrel jack that we're seeing on screen right now, I think that's a reasonable representation. It's got like the third pin. There is 3 pins on this. Whatever I use needs to have 3 pins. Now the middle pin is not shorted by the look of it. No, it's not. So that's just a 2-pin jack. That's not going to be good enough. So I think this one here is what we're after. Definitely think this is the one that we're after. So let's click on OK. Let's place that in our diagram. Now the question is what pin does what? Okay. We also need, let me just save this a moment. I got to think about how I'm going to get, so this is bringing in 12 volts. Okay. So I'm computing. I think I have this wrong. But we'll fix it in a second. So let's have a look. I need a capacitor. And I need a power regulator. It's a polarized capacitor, so let's plop it by there, like so. And I need a power regulator. Now, I've got to figure out what power regulator I'm using. I keep forgetting the power regulator's reference. I got the power regulator in my parts bin, or is it in a cut tape? I think it's in a cut tape. So that's another thing, right? So components can come in a variety of different packages. So you can get a package of like a bag of components, and they're loose, or you can get them in cut tape. So these cut tape arrangements effectively are for use with pick and place machines like the Lumen P&P that we're in the process of building. Let me see if I can find my power regulator. Is that a power regulator? I believe that's a power regulator. It is! Right, I got to identify it. Ha! Okay, because I got to make sure I choose the right device. Let's bring in the microscope again. What component do we have, guys? I wonder. So you see this perforated tape? That's where the machine grabs it and drags it along and feeds it into the machine. Right, so we've got an L392, an L392 power regulator. So let's have a look at the data sheet for an L392 regulator. What am I looking for? There we go. Right. L392. 392 regulator. Is that what it is? Let's check this data sheet. I know that it is a SOT23 package. Yeah, whatever. That's not it. That's not it. Okay, SOT23. Hello. There you are. This is a low voltage dropout regulator, 3.3 volts. Okay. Now I could cheat because I have done this before, right? I have used this component before. So let me cheat a moment. Let's open another instance of KiCad. And I'm going to open up another project. Oh, there it is. Schematic Editor. Okay, so it's an SPX3819M5L-3-3. But of course it is. Like, duh. Right, let's place this voltage regulator. And if this is going to get us out of a bind. So there's the one. That's the one I want. Okay, so place symbol. And it's an SPX. There it is. So it's an SPX 38195M-L-3-3. Okay, cool. So we get the footprint and we get everything that we need, right? So let's bring that in, plunk it there. Okay. So I'm going to put that in the top corner, and I move this to here. That to there. We're going to just wire this up now. Oh no, is the redeems off? I'll refund those points, buddy. I'll refund those points. Okay, so we want a ground in here. So let's grab a ground, copy paste. I'm going to make this element of the jack. I may need to play with this to get this just so, but we're going to. I think that represents the center pin, which I think is VCC. And then this pin here is ground. So we're going to tie this pin here to ground. Copy paste and bring a ground in here and a ground in here. And let's just draw the lines, the wires between these components in. All right. So we've got an input and we've got an enable pin. So let me move this to Shah. And this is why I'm starting to think I've got this wrong. Okay, and so though that essentially ties everything. It enables the voltage regulator. It says, hey, you're good to go, right? And then we get this here. BP is not used. So I can draw a line here, bosh, like that. And then we can go another line. We want 3.3 volts. All right, and then we draw a line from our 3.3 volts to the top of the capacitor. And we're almost done, right? Because we're essentially switching ground. So this is what I've messed up on, right? This is what I've messed up on. So this line here, I'm going to just tee off. And this is going to be referenced as 12 volts. So let's put a power reference in here. This is 12 volts. Oh, that's negative 12 volts. I don't want negative 12 volts. I want positive 12 volts. There we go. Bosh, like that. Okay, and this is where I messed up, right? Because we're switching ground. We are switching ground, not switching live. I need to double check this, but I'm pretty confident. Yeah. So if I look at my board layout here, right? The LED is connected to my VCC line. And in this case would represent 12 volts. That's the logic, right? That's the logic of what we're doing here. This would be 12 volts. Connects to the MOSFET, and the MOSFET then connects to ground. And then when we apply a positive voltage to pin 1, it connects the source and drain to ground. Okay. So that's where that's at. So I made a mistake, but I caught it. I caught it. So let's get rid of these. Let's get rid of that. Yeah, I tell you what we're going to do. We're going to copy the channel names. We're going to delete them. And delete these wires. We'll fix this up right now. Okay, so we're just inverting what we've done previously, right? Because I'm a doofus. But at least I caught my mistake, right? That could have been a problem if I bought these boards and I'd had that mistake, then that would have not worked out well for me, right? So we're just putting the channels onto the odd pins. Okay, like that, because that would represent our ground, right? That would represent ground. Switched ground. And then we want to bring in a 12 volt plunk that down here. Put it there, right? And then we can draw a wire from this one to there, this one to there, this one to there, and this one to there. And then we fixed it. Hey, we fixed it. Now, I've got a reasonable expectation that this is going to complain, right? Because we don't have any power flags or anything like that in the system. So I think that's probably what I need to do next. Is this a power flag? Hierarchical labels. Okay, let's put in a power flag. Let's see if I was to do a check, right? Let's see if it'll flag it. Footprint assignment. Electrical rules check. Okay, run ERC. Okay, we've got 16 errors. Okay, so my label TX and RX is not going anywhere. So we do need to break out TX and RX so that we can have some programming headers. So we got some lanes here that are not marked with anything. So if we let's fix those, right? So we'll just bring those in like that. Oh. Bring this line in to here, like so. And then we just use this not used reference, right? So we just plop those in to there. Same with the Mosey and serial clock pins. We're not using them. So we have to explicitly tell the software, hey, I know these pins are here, but just like ignore them, please. So we're going to see a bunch of errors go away now. Okay, so we've now got 9 errors. Oh, we missed a pin. Okay, let's get rid of that. Let's run the rules check. Okay, so we've now got 7 errors, no warnings. So TX and RX we know about. We got to put a header pin on there. Where else have we got problems? You got problems. Right. MP. Okay, so we can probably just mark that as not used. Bosh, like so. If I run that, it should go away. It does. Okay. So it's now saying it's starting to complain about power. Okay. So we got 6 errors. So what we're going to do is, I think, if I copy, we got all the elements, right? So if I copy this, put it there, copy that, copy 3.3 volts, Let's rotate it. And then we copy a ground. All right. So if we go into our power symbols now, we should have flags. We need to use flags, power flags. Where are the power flags? Oh my word, my brain is shot. Where's the power flag? I'm not surprised. Hey, Ishwood, I'm not surprised at all. Okay, let's run that rules check once more. All right, I need power flags. Add hierarchical label. No. No. Place the flags in here. Power flag. So if I rotate that, put that there, and then we go copy paste, we put one there, and we go paste and put one there. So now if I connect these, I'm hoping all of my power issues go away. Right? So we're telling KiCad that these symbols represent power. So now I've got this dedicated section for 12, plus 12, 3.3 in ground. I'm reasonably confident that that's going to be happy. Right? So let's run the rules check. How are you doing, Ishrid? Hope you're doing well. Okay, so we now have... Okay. Maybe I only need to add it to... Maybe I only need to add it to 12 volts, right? Let me just trigger this again. Run ERC. Okay, so the two warnings of TX and RX. Nice. You got some back pain to deal with. Dumb co-workers in high ranks. Just the daily normal. I hear you, man. I hear you. So we're live streaming on Twitch and YouTube tonight. And we're doing a bit of work for controlling my lights. We actually have a sponsor for tonight's stream, and that's PCBX. PCBX is a PCB manufacturing company. As I mentioned earlier, if you need software like KiCad and you're not familiar with that, and you don't necessarily want to go to the extent of installing the software, PCBX has an online tool that you can use to draw your schematic, your board outs, your board layouts, get your 3D models of your circuit boards, and also order directly from the website. So check out PCBX. Links are in the usual places in the description below if you're on YouTube. Or if you go to About on Twitch, it's in my panel section. Okay, so let me just double check a few things here. So we've got 12 volts down here, perfect. Switch grounds. I think the only thing that we need to do right now is to figure out our TX-RX problem, which is here. It's telling it they're not being used. So let's place one more component. And this will draw our schematic to a conclusion. We want a connector. We want a connector which is 1x4. Okay, we'll click on OK to that. And this will be our programming headers, right? So let's plop that there. Let's grab a ground. We know our device needs 3.3 volts, so let's grab one of those. We know we need TX and RX. Well, we'll come to that in a second. So let's just place 3.3 volts by there. Let's place ground by there. Let's draw the wires that we need to connect these. And let's put some wires for some labels. Now, one of the things that is, again, it's a little bit of my style of how I do things. I don't like having ground and VCC or voltage next to each other because I like to do stuff on breadboards. I like to pull things around. Sometimes my soldering isn't great and I don't want to short anything out. If I place the components, the VCC line and the ground line at opposite sides, then they can't short with each other, right? They can't short out and it's not a problem, right? So these pins are voltage tolerant. So if I short these 3.3 volts to TX or RX, it doesn't matter. Equally, if I bring it to ground, it doesn't matter. Nothing gets hurt. But if I short 3.3 volts to ground, I can cause problems pretty quickly. Right, so let's get our programming labels in. So let's grab our TX, copy, and we'll just place it in here, paste, rotate it until we get the orientation that we like. So let's put it like that, then it's nice and neat. Let's grab RX, we'll copy, we'll paste, we'll rotate, and then place. And now if I do my rules check, I should find that we get nothing. Bingo! Green all the way. Close and save. Right, so that's mostly everything done. Let's grab this. Let's bring this in towards the microcontroller. Let's put it in the realms of the microcontroller, right? So we know that's all to do with this. In fact, I'll tell you what we're going to do. We're going to move it right all the way up here. Just going to organize our drawing a little bit better. All right. So we've got our power delivery. We've got our logic control in the microcontroller. We've got our programming. We've got our inputs and outputs. And then we've got our driver circuits. So now what we've got to do is we've got to assign footprints. So let's have a look how we do this. So to assign a footprint, we click on the Assign Footprint tool, and we get a new window pop up. Now, depending on the libraries that you've used, some of these will actually come with things already defined. So the only thing that we know that we've got defined properly here is the ESP12 module. And we're going to keep that. And also this SOT23 package. Everything else is bad, right? So can I delete those? Yes, I can. So let's get rid of these. Okay, so my LEDs, I know the majority of the components I'm going to be using are 0805 standard. So if I grab an 0805 footprint, then we should be good to go. So 0805 SMD metric, right? So I can choose that for my LEDs. I just double click now. And these are assigning the footprints. My LEDs are also 0805s. So that's good. My pin headers. Okay, so connector, I want connectors. Pin header, here we go. There's lots of things in here, right? So pin header, we know they're, what's the spacing on these pins? Oh my word, my brain is just gone. Is it 2.5 something or other? 3 point? It's 2 point something or other. So these are 1.27. These are 2 millimeters. Then the next one up. It's the next one up. 2.54. There we go. Pin header. 2.54. And this is a 1x4. So let's go 1x4 vertical. Let's pop that in there. Cool. And we've then got our 8x connector. We're in here but at the same time, so let's pop that in there as well. Let's find this pin header in the mix. It's seeing things, so that wood for the trees, right? So there we go, that's in there. We may need to play with these just to make sure that we get the models, but we'll worry about that when we do the board layout. I just want to get the schematic piece done, and then we can call it quits for tonight. The push buttons, let me just double check on my other drawings here what I used for my push buttons. I think I might have it. Excellent. Cool. Okay, so these are my buttons. So let's pop these in. And these are all surface mount push buttons. The barrel jack and, right, so the capacitor. Okay, I need to close that project because I know it's got changes. I gotta find the right components here, so I'm kind of rushing through the library. So file, open project. I know you guys can't see this, right? So I'm just looking at another project I did because I know that the component I want to use is in there. Open recent. I think this is the project. Let me just open up the PCB. I think this is it. I need to be doubly sure before I pull the components off it. Yes, perfect. All right, so let's go into the schematic editor. Let's load up my footprints. What did I use? What did I use for my power? There it is. Got it. All right, let's bring this in. It's a oh God. I can't pronounce it. Tantalum? Tantalum. It's a tantalum capacitor, right? So that's that. The barrel jack I'm not too sure about. So it's got to be a... We'll look at those in a second. N-channel MOSFETs. N-channel MOSFETs. I got to find the package details. Where did I put my MOSFET box? In there? No. No. In this bottom one? Yes. Okay, does it say what package they are? No. Of course they don't. Right, so it's these MOSFETs that we need to figure out the package of. Okay, so let's get a browser open and let's hunt down my component. So this is an IRLZ 34N, go. Okay, so let's get a data sheet on this. And this will tell us the form factor that this is. Yeah, whatever. Continue the site. Right, okay, so package, please. It's a TO220. That's the package, or the case. So if we now go back into PyCAD, we should hopefully be able to find a TO220 package. It's a through-hole THT. I would say it's vertical. It's a 3-pin. So let's view the footprint. And that's it, right? Perfect. That's exactly what we want. So we just select that. Awesome. Now the barrel jack. This is the kicker, right? This is the one that we're going to have problems with. And is that horizontal? It's not that one. All right, so you can just right click, select view footprint. It's not that one. We got one with... Okay, we know it's a through hole, right? So... Right, it's not that. I may need to go through these one by one. Barrel jack, horizontal. There we go. That's the puppy. All right, so we go, click OK. And now we have all of our components, right? And the footprints. So if I now click on this little icon here, we're going to close the loop. We're closing the loop. So we now have our board layup tool. And the first thing we're going to do is import graphics. We're going to select projects, board outline. We're going to put this on our edge cuts. And here is our circuit outline. Let's grab, I'm going to grab a few wires here, and I'm going to, Control Z. we're going to get rid of a bunch of these lines because we do not require them because they're surplus. They were reference. There we go. Right now, if we click this button here, update PCP with changes to schematic, we should bring in all of our components. Okay, no net found for J2 pin 3. Okay, so it's complaining that a net on J2 pin 3 is not right. So there's all our components. Let's see if I can just get these components on the board and I can show you something pretty cool. Just oddsing these around. We're going to have fun trying to make all of this fit on here, right? I got a sneaking suspicion we're going to be putting things on the back. Yeah, we're definitely going to be putting like SMD components on the back. In fact, let's do that right now. Flip. Yeah. So they're now on the back. Okay, so that's those there. This is going to be pretty cool, right? When I do this, I promise it will be. As long as it works, right? As long as it works. Yeah. Okay. So what we're dealing with here is both sides of the board. And I've got to find some way of jamming these in, right? This is going to be fun trying to get this all to fit on the board. I'm just trying to make it like fit the space right now, and it's problematic. Okay, move, rotate. Okay, we're getting there. I'll do. Why is that text been left out there? Why have you been left hanging? Get back there. Okay, so now I've got this laid up like this. I can let it go. Right, I can go into my viewport and go 3D view. And if I've done this right, we get to see a circuit board. We're getting closer to seeing what this is going to actually look like. How slick is that? Obviously, I need to finesse this a little bit better, but this we're getting pretty close, right? To being able to get this board set up and ready to be sent out for manufacture. Like I say, this is very much a loose sort of mock-up. Just throwing these things in here. Now, I probably want to space these MOSFETs out a little bit so there's a bit of room for some heatsink, should they be required at a later stage. But like I say, we're only going to be doing a single channel for my purposes. Right, iFrog, and that loops us right back to where we originally started, right? So as I mentioned, we do have a sponsor for this stream, and that is PCBX. PCBX is a board manufacturer that does a number of different things, and each of the board manufacturers have their own unique selling point. And PCBX is no different. So you get your usual sort of, you can select a bunch of options from 1 to 4 layers in terms of your boards. You can have PCBX fabricate your PCB. You can choose various different solder mask colors, board weights, all of that sort of cool stuff, the stuff that you would expect. But one thing that PCBX also do is they have an online EDA designer. So if you don't want to use something like KiCad, maybe your computer isn't powerful enough to run the EDA that you want to, right? They do offer a web-based version of the EDA that you can create the schematic like we've done, the board layup, the 3D view, and order directly from this web-based tool to design your circuits. So if you want to check out PCBX, they are in the links in the description below on YouTube. And if you're watching on Twitch, if you go to the About section, there is a panel that gives you a link to PCBX.com. So thank you very much to PCBX for sponsoring this stream. And hopefully we'll be seeing the results of the board manufacturing process, and hopefully some more projects in the future. I've got quite a few things waiting in the wings. It's going to be really, really cool. So excellent. So that brings the stream to a close. Thank you so much for everyone hanging out. I will be streaming again next week, where we will be putting the elements of the Lumen PMP motion system together. I am now in possession of the linear bearings, so I need to make sure that they're going to fit and make modifications where necessary. But we're very close to having the Lumen PMP. The frame is together. We need the mechanics of the system to be together. So we're very, very close on that. So, until next time, have fun, be safe. I will catch you in the next live stream or YouTube video. And don't forget, if you've made it this far, to hit the subscribe button on YouTube or the follow button on Twitch. Both of those actions are free, so thank you so much for your support. Are we going to raid out? No, not tonight, iFrog. But until then, I'll catch you in the next one. Bye for now.